Now, the next chapter is the properties of expectation. We already know a lot about expectation. We have seen the formulas, we have seen how it's used, etc., even conditional expectation up to a degree, but still there are lots of mysteries for expectation for us to, solve. Let's do a little recap and remember what it was. Now, for discrete random variables, expectation was calculated by multiplying x and px, the PMF, and then summing it over all the x values. And for continuous random variables, it was x times PDF, the fx, and then integrating it from minus infinity to infinity. Now, any value for x is, going to, it's going to take any value between a and b limits, a lower limit and b upper limit, as long as they are the limits of the, probability as well, which can be written like this. If we set the probability of x being between a and b is 1, then all the, probability values will be, all positive probability values, let's say, non-zero probability values will be taking place between a and b, which will in turn, end up making sure that the mean, the weighted average, which is the, expected value, is between a and b as well. Now, we know that there can be more than one variable in a PMF or PDF, which is a joint PMF or joint PDF. So the expectation of these joint versions are written like this. So we already know this one actually. For one variable, which was, for example, for 2x plus 5, we could have, done the calculations to, calculate the expected value, but with two random variables and with a joint, density or joint PMF mass function, we can do this the same way. So we actually have something here like x and y, a function of x and y together, times the joint PMF of x and y, or the function of x and y together times the joint PDF of x and y. And this is the same thing. And again, we have two, double integrals or double sums over here. For example, now we know that an accident occurs at a point x, which is uniformly distributed over a line L, a road length of L, and there's an ambulance on that road as well, and this one is uniformly distributed as well. And these two distributions, these two, events are independent. We know that those values do not affect each other. So it's asking us to find the distance between that ambulance and the accident. Now the thing is, as they are independent, their joint PMF or PDF in this case is going to be the sum multiplication of their own PDFs. And as they are both uniformly distributed over 0 to L, their PDF is going to be 1 over L, for both of them. Hence, the joint distribution function is going to be 1 over L squared, as you can see here. And then the value we are looking for is the distance between those two things, the accident and the ambulance, is going to be calculated with x minus y, absolute value of x minus y. Why? Because we know that x is the place where the accident has happened and y is where the ambulance is at that moment. So the distance is going to be their difference, but we don't know which one is greater and which one is lower on the scale from 0 to L. So we can just take any one of them as the first one and subtract the other one and take the absolute value, which is going to give us a positive number anyway. Distance should be a positive number, so it's going to give us a positive number anyway. So we are looking for the expectation of this absolute value, and we have this joint PDF. So we know that both x and y are between 0 to L. So all we have to do is just calculate this one, this little integration. Now, the integration is going to from for y and x, and 1 over L squared doesn't have any x or y values, so it's just going out of the integral like this. And we have to integrate x minus y, absolute value of x minus y. Now, we can integrate this for y. We have to take into account, is y, we have to ask this question, is y greater than x or lower than x? If it is lower than x, then x minus y is going to be, is going to stay like that as x minus y coming out of that absolute value. But if y is greater, then this will switch to y minus x. So let's assume that x is greater and y is lower. So we're going to get this one. Y is going to be from 0 to x as it's lower than x. and this absolute will come out as x minus y dy. If, on the other hand, if y is greater than x, then our integration limits are from x to L, because it's greater than or equal to L, and the integrating value, the value we're going to integrate, is going to be y minus x, the opposite, the negative of this absolute value. So we will get this one, and their total is going to give us this formula. Now, this is just for this L square over 2 plus x square minus x times L. This is just this first integration. We haven't done the second integration yet, so we have to integrate this one once again for x with respect to x. So we integrate this one and we get L over 3. So at the end of the question, we see that the difference between the ambulance and the accident, the expected distance, is going to be L over 3, 1/3 of the whole road. So we can talk about, we have talked about some of random variables before. Now we're going to talk about its expectation. We had done this before and we have seen the joint formula and it was calculated. This part, this little, let's say, formula or lemma or whatever we call it, is actually very important, because it says that as long as Ex and Ey are both finite, so they don't have a value of infinity, as long as they are both finite, for the function x plus y, the expectation of x plus y is equal to expectation of x plus expectation y. So we can just separate those expectations. It says that we can write it like this. Now, we have already seen this with scalar numbers. For example, we know that expected value of x plus 5 was the expected value of x plus 5. So, or anything like this, okay? So we already know this happens, but this is with 2 random variables or more. So we know that we can write it, instead of writing it like this, we can write it like this. We're going to use this one to get, some, let's say, methods, to form some methods to be able to solve some questions that needs, a special method like this to be solved. You'll see. Some, things will be easy as well with this one. For example, it says that let x1 to xn be independent and identical distributed random variables, okay? Having the distribution function f, okay, we don't know the distribution function, but they all have the same distribution function, and expected value mu, all right? Such a sequence of random variables is said to consider a random sample from the distribution f. The quantity defined by x bar, this is x bar, is equal to xi over n, I from 1 to n. So it's just taking a sample, okay, from all the random variables and just dividing it by n. We have n samples over here. So this here is called the x bar, and it says that this is called the sample mean. Compute the expected value of the sample mean. Now, to compute this one, we'll just put an expected value function over here and here as well. When you put an expected value function over here for x, we know that it's got to do something with x. So this n is going to come out. So you can just write it like this one. You can just write it like this one. Okay. As you can see, when you're talking about the expected value of this one, x bar, you're talking about the expected value of this one as well. So this n goes outside. Now we have only left, we only have the summation of xi, summing every random variable and taking the expectation of these. So instead of this, we have seen in the slide previous that we can just take the expectation of every random variable and then sum them together, which can be written like this. And we already know that this one is equal to mu. So from I equals 1 to n, we have mu items, which is n times mu, multiplied by 1 over n. The answer will simplify and we will get just mu. Now this one is the basic but the hardest, actually, at the same time examples, I would say, because if you cannot understand this, the other ones will not be able to make sense for some time. Now we already know how to calculate this question by using the expectation of the random variable we know, which is hypergeometric, which we will see in a second. But still, we have to use this new method we are devising here. If n balls are randomly selected from an urn containing n capital N balls, of which m are white, find the expected number of white balls selected. Now, usually We just select those balls and just calculate the probability to find the PMF and then find the expected number of white balls. It can be done. But here we are going to form a new method. This is this hypergeometric, but we're not going to use the hypergeometric function in here yet. So we're just going to say that we are forming a new, let's say, random variable, and we're going to call this random variable xi. And this xi is going to be 1 if the ith white ball is selected. Okay, we have a total of m white balls, so we have a total of m, random variables from x1 to xm. Okay, and this random variables, total of these random variables will give us x, which is the number of white balls selected. So, for example, if we have x2 as 1, then the second white ball is selected. If we have x5 as 0, then the fifth white ball is not selected. So we have a total of m random variables, and their sum is going to give us the number of white balls selected, which is logical. Now, as you can see here, these are the m random variables, and their total is giving us x, and each random variable is 1 if that white ball is selected. The white ball related to that random variable is selected, and 0 otherwise. Now, from here, we know that we can calculate the expected value of this xi. Okay, we just need to find the probability of getting 1 and multiply it by 1 plus probability of getting 0 and multiply it by 0, which is gonna drop down. It's gonna go away. So from here, we don't need to use this term because it's 0 times something. We don't even need to calculate this one. Over here, xi is equal to 1. What's the probability of one white ball getting chosen? Now we need hypergeometric, which is 1, choose 1, and capital N minus 1, choose N minus 1, and capital N, choose N. Now, this is going to give us N over capital N. This is the expected value of one xi, any one of them. Okay, for every one of them, we have total of m xis. So all our expectation, the expectation of x is going to be the sum of all these expectations, and all these expectations have a value of n over n. So we have m times n over n. This is the first method. The second one is very similar, but it's a bit more different as well. In the second one, we are saying that instead of xm, we have yn. We are selecting balls, so we are just checking those balls. Is the first ball I selected white? If it's white, let's give it 1. If it's not, 0. If the second ball I have selected white, if it's white, give it 1. If it's not, give it 0. Goes on like this. So now we have y1 to yn because we are picking n balls. So we have y1 to yn, and this total is equal to x, which is the value we are looking for. Now, yi is equal to 1 if ith ball selected is white. Okay, I'm selecting a ball, I'm checking if it's white. If it's white, then this is 1. If it's not, then this is 0. Then I can write the expectation of yi like this: 1 times the probability of yi being 1 plus 0 times something. It doesn't really matter what it is because it's multiplied by 0, it's going to follow. So we are looking for this value, yi equal to 1. Ith ball selected is white. Okay, this is actually m over n because we already know that we have m balls out of n balls, and the first time is m over n. And the second time is going to be m over n as well, because we don't know what happened in the first one. And the third one is going to be the same, and the fourth one is going to be the same. We know this one. We have seen examples before. So this is my expected value for just one yi. For every n yi, for every yi, I'm gonna sum those n times. So n times m over n, which is the same as the previous answers, because it's the second solution anyway of the same question. And then we have the fourth one. Now, we already know this question. We have m people, they are throwing their heads into the middle. The heads are scrambled and everyone picks one randomly. What's the probability, what's the expected value of expected number of people that select their own heads? So we already know that we're going to have to create an xi, something that we're going to sum up. So we're saying that for every person from 1 to n, there is a random variable that's showing if he or she has gotten his or her hat. So if the first person has gotten his hat, then it's 1, x1 is 1. If the first person has not gotten his head, then x1 is 0. If the second one has gotten his head, then the x2 is 1. If the second one has not gotten his head, then x2 is 0. Something like this. Now, we already know the summation of these x values is going to give us the x. The original x. Now, the xi is 1 if his x1 head is 0 otherwise. Now, we know that the expected value is still 1 times px1 and 0 times px0, which in this case, this is going to fall as well. So we just need to concentrate on this one. Xi is equal to 1. Now, for any person to select his own head, the probability is 1 over n. So I have n random variables. They all have the same expected value, 1 over n. So that their total expected value is going to be n times 1 over n. It's going to be 1. So we are just looking for one person to pick his own, we're expecting one person to pick his own head. Just one person. So covariance, the next one. Now, we have already seen variance. We know alpha about variance. We know that it's related to expected value. Now we are seeing covariance. Now, covariance is as well, just like variance, it's a measure of your, spreadness, chaos, whatever, how, spread out you are, how distant you are from each other, etc. But this is for two random variables now. Covariance takes into account two random variables over here. Now, for x and y, covariance between x and y is little like this one. Now, as you can see here, this should be very similar to, things you have known. If you replace y with x here, you're gonna get the expectation of x squared minus ex squared, expectation squared. So this is actually the same as variance, where covariance is xx. As you can see, it's the same here. Covariance x is equal to variance x. For covariance xy, covariance yx is the same thing. I can just switch places. And when there is a scalar value in one of the random variables in the covariance, like for example, covariance of ax and y, then this a comes out, a times covariance of x and y. And the last one, this is just like the expected value. Instead of summing the random variables and then taking the covariance, you can just take the covariance and then sum them. Sum the covariances instead of take the covariance of the sum. It gives us the same thing. Now, there's an example over here, which is actually something we know very well, but we're going to use this variance of sums. Now, take a look at this one. There's a binomial random variable x with parameters n and p. So we should find the variance of binomial, the variance of binomial random variable. Okay, we already know the solution, n times p times 1 minus p. But let's stay there. We're going to have to use the variance of sums. So we know that x is divided into n parts, n trials. So we're going to take our new, let's say, random variable from 1 to n, x1 to xn, like this one. Now, they are all Bernoulli trials now. Each random variable, each of these random variables are independent random variables, are independent Bernoulli trials. So we're going to have to find the variance of each one of them. To find that, we're going to have to find the expected value of each one of them, and then the expected value of their square. Now, as you can see, x1 is 1 if I try success, xi is 0 if it's a failure otherwise. So we know that from here, from this equation, the variance of x is equal to the sum of their all variances. So to find the variance of any one item, any one random variable, we need to check these two formulas. Okay, we're looking for the expected value of xi and the square of expected value. Okay, then square root of expected value and x squared is expected value. Now, we know that x squared is equal to x. Why? Simple, because x is 0 and 1, then x squared can be just 0 and 1 as well, and in the same conditions. So xi squared is equal to xi. So I can write xi instead of xi squared over here. It's going to give me expected of xi minus expected of xi squared, which is p minus p squared. Now, this is just for one item, one xi. For all the n xi's, we have n times p minus p squared. If we take this into parentheses of p, we will get np times 1 minus p. Now, conditional expectation. We have two discrete random variables, x and y, and we are looking for the conditional expectation. We have already found the conditional, PMF before. We know the conditional joint PMF is written like this. They joint PMF over the, PMF, marginal PMF of the condition. Now, from here, we can write the expected value of this condition. Okay. So, for example, expected value of x given by given y is equal to y. Now, to write this, we need this one. Okay, but this is also equal to this one, so it's not really important right now, but still, we need this one. We need to multiply x, which is the expectation we are looking for, times this value, which is going to give us this value anyway, same thing. If x and y are independent binomial random variables with identical parameters n and p, calculate the conditional expected value of x given that x and x plus y is equal to j. Now, we already know that x plus y is actually, let's say, binomial random variable with 2 n trials and success rate of p. We already know that. So it's asking us to find the conditional expected value of x. Now, as it has given us x plus y is equal to j, we can just say that, okay, let's give x the value of k, then y is going to be j minus k. We can start from there. So you can see y is going to be j minus k and x is equal to k over this value. X plus y is equal to j. Now, coming back here, we already know that x equal to k, probability of x equal to k is just putting in this one, or whichever k you want, into the formula for k. And they are identical binomial random variables with NP. So I'm just gonna look for k successes in n trials and a binomial random variable, which is gonna give me this one. And j minus k successes in, again, p success rate, we're gonna get this one. And this one over here, x plus y is equal to j. Now, as I said earlier, x plus y is actually a binomial random variable with 2n and p parameters. So we're gonna have to use this 2n, which is gonna give us 2n choose j, pj, q, 2n minus j. Now, when we simplify all of this, okay, we just get the combinations out, type the combinations, find the formula, we're gonna get j over 2. Okay, this is gonna give us the conditional expectation. Now, in the second part, we are looking for the conditional expectation in continuous random variables, which is the same as the discrete random variables, but over here, the main difference is, as once again, the integration. We have to integrate from minus infinity to infinity. Now, this part is the key part in this chapter, I would say, computing expectation by condition, because this is what the midterms or finals are about. Most of the time, we are asking a question from here for sure, but sometimes it skips one or two, tests or exams. Now, over here, it says that the expectation of x, the expected value of x, is equal to the expected value of x given y. Now, this one is equal to this one. How can we be sure? We just need to prove it. Okay. Though we don't think this looks like equal at the first, look, you will see that it's the same thing anyways. Now, expectation of x given y, another expectation of y. We're just gonna write this one. Expectation of x given y times p to the probability of y is y. Now, we know that from here, we can just, prove that this is correct, okay? We just need to prove that this is correct. It's equal to this one. Now, from here, we need to see that we can just open up this part. Expected value of x given y is equal to y. This one can be opened up like this, as you can see. This is the formula. We're just writing the formula over here. Then we know that we can write it like this. Now, this is the joint, conditional formula, and now we know that this is actually written with joint PDF over joint PMF over here, of course, joint PMF over the marginal PMF. So joint PMF over the marginal PMF of y. Now as you can see, these two values are the same and they're going to simplify, and we're just going to be left with this one, as you can see here. Now in here, I want to make sure that you do see this one. Instead of yx, we would start with xy. So we're going to sum over y first, then we're going to sum over x. Now, when you sum over y, we're going to summing these values. You can think of it like this. You are summing every y value, and you're getting something dependent on x. You're just removing y from the combination entirely. You're just trying to find the margin of x, actually. So when you find the margin of x, you write it like this. Now what you have is summing over x times margin of x. Okay, this is the formulation for expected value. So this is going to be equal to ex. Once we can see that ex is equal to this one. Now a simple question, not that simple to read and understand, but simple to solve at least. We have a miner trapped in a mine containing 3 doors. The first door leads to a tunnel that will take him to safety after 3 hours of travel. The second door leads to a tunnel that will turn him to the mine after 7 hours. After 5 hours of travel, the third door leads to a tunnel that will turn him to the mine after 7 hours. If we assume that the mine is at all times equal likely to choose any one of the doors, what's the expected length of time until he reaches safety? Now, in here, we have 3 different doors, okay, which means 3 corridors. We are taking one of those corridors. We are just moving around and coming back or going out. There's a 1 over 3 chance of going out and 2 over 3 chance of getting back after losing some time, 5 or 7, depending on which one we choose. So what we need to do is just write in the formula, okay, the conditional expectation formula. As you can see, the expectation of x is equal to the the summing of all the expected values over here. What happens if I choose door 1? What happens if I choose door 2? What happens if I choose door 3? We're just gonna sum all those values. And as you can see, this expectation, choosing first door and then sticking to first door, going to the first one, coming back. What's the expected value now? Now, in here, you can say that you have chosen the first door, so your time of travel is going to be 3 hours and you're going to be out. So this is just 3. Yeah, simple as that. But in the second one, in here, what happens if I choose the second door? Now, if I choose the second door, I'm going to get out, tour around a bit for like, I don't know, 3 hours, 5 hours, 5 hours, and 5 hours later, I'm going to be back at my starting point. So I'm going to lose 5 hours and be back at my starting point. So this is what I'm expecting here, 5 plus ex. What about the third one? Now, in the third one, I'm picking third door. It's going to be, making me go around for 7 hours before I come back. So when I get back there, I'm going to have to check what happens, and I will see that, oh, okay, I'm back to where I belong, so I have to start once again. To do that, okay, of course, I have to, add this into the equation as well. 7 plus ex. Now, all these values are calculated from, conditional probability, conditional expectation. And we also know that this was equal to ex at the start anyway, so we're going to have to simplify the ex values and just get rid of all those numbers, and you will see that ex is equal to 15. So starting the exercises now. The first one is roll for die once again. I repeat the roll 2 fair dice. If their sum is 6 or lower, I wait for a time equal to this sum in minutes and roll again. If their sum is 7 or higher, I stop rolling and record the time spent as t. Find the expected value of t. Now, we have to find how we can wait, in which condition we wait, how long we wait, with what probability, and what happens if we roll 7 or higher. Now, with 1 over 36 probability, we're going to roll 2, which means that we're going to wait 2 minutes, and then we're going to restart the trial, because it's going to be the same thing rolling again. With 2 over 36 probability, we're going to wait for 3 minutes and then restart the thing all over again, once again. With 3/36 probability, we're going to wait for 4 minutes, roll 4 and wait for 4 minutes, and then re-roll once again. With 4/36 probability, we're going to roll 5, wait for 5 minutes, and then re-roll. And with 5/36 probability, we're going to wait for 6 minutes because we have rolled 6, and then we're going to roll again. Now, the rest from 7 to 12, which is 21/36 probability, is going to be ending the game. You're not waiting anymore. So what we have here is like this. The expected value of t is actually equal to 1/36 times 2 plus et. Why? We are waiting for 2 minutes because we have rolled 2, and now we're restarting. So when you restart, your expected passage of time is going to be the same, okay? The expectation of t. On the other hand, with rolling a 3, you get 2/36 chance of doing that, and you wait for 3 minutes, and then you restart. And again, for 4, 5, and 6. If you roll 7 or higher, the game ends. So you don't spend any time, 0. The total of this one is going to be subtracted. The ET total, at least, will be subtracted from this one, and we're going to get ET value as 3.33 on 10/3. Now, this is the average, waiting time, the mean waiting time. In the second question, well, this one is a bit more complex and a bit harder than the first one. It says that Sam and Dean Winchester are chasing a Wendigo in an abandoned coal mine. They have 3 hours to find its lair before one of the victims there die, and they are at a crossroads. Okay, 4 different paths. Each 3 of the 4 paths lead to an unsuccessful chase and make them lose 1 hour and return to where they were. And one of the 4 paths lead to the Wendigo's lair in 45 minutes. They prefer to chase the Wendigo as a team, but they can also split up and search solo. If they will always choose the paths with the same probability, and x is the time spent searching for the layer, what is the expected value of x? Now, in here, we have 2 scenarios, going as a team or going solo. They prefer to go as a team, so we will check the expected value of going as a team. If going as a team is better than 3 hours, has expected time of less than 3 hours, then they will go as a team. But if they have a value, time spent which is greater than 3, the expected time spent is greater than 3, then they're going to search solo, and we will see what kind of time they spend if they are searching solo. Now, for the first part, we know that if they choose a wrong path, they're going to lose an hour. But if they choose the right path, they're going to do this stuff in 45 minutes, in 3/4 hours. So the probability of picking a wrong path is 3/4 because there are 3 wrong paths and 1, right path. So it's 3/4, and picking the right path has a probability of 1/4. So from here, I know that the expected value of t, which is here x, of course, the expected value of x is going to be 3/4, picking the wrong door. 1 minus 1 is because you lost 1 hour, ext. Now, this is the same thing over here because I have lost an hour and I have come back and I don't know which door I'm going to choose again. It's totally random. So we don't know how to proceed with this one. So it's the same thing actually, ext. But on the other hand, there's a 1/4 chance that I will just finish this in 45 minutes. This is going to be done. We're going to find the layer in 45 minutes. So this total should be equal to this one. As you can see, we will just subtract this xt in 3/4 from this part, and then multiply everything by 4, and you will get 3.75 hours. Now this is greater than 3 hours, which means that they have to search solo. They will have to split up. So if they split up, there are 4 paths and there are 2 of them, so they will choose 2 different paths. There are 6 different ways of doing this. If you call the paths A, B, C, D, it's A, B, A, C, A, D, B, C, B, D, and C, D. 6 different paths to choose from, path pairs. Then, out of these 6 paths, there is only 3 correct choices. So, for example, if the correct road is A, there's A, B, A, C, and A, D. 3 different paths going to the correct choice. So, it's 3/6, which is 1/2. The success rate is 1/2, so the failure rate is 1/2 as well. So, with 1/2, we are looking for 1 plus the expected value of solo, going solo, plus 1/2 times 0.75. which is going to give us the solo, finding the right path, the expected value of finding the right path solo, 1.75 hours, which is better, much better than 3 hours. Now, in the third one, again, we are at a crossroad, and there are 4 leads that will go to your room. Every room has a button in it, so you go to your room, you press the button, and you come back. This takes 2 minutes, and each time you press the right button, there is an order to those buttons. You have to pick them in the press them in the right order. Each time you press the correct button, that door and that corridor will vanish. Okay, you will have completed that stage, and you're gonna have to keep going with the next stage. And if you do something wrong with the next stage, you're not going back. Okay, that door is gone. You have completed successfully. You just need to keep going and going. So, in this context, in this exercise, at the start we have 4 paths, which means that we only have 1/4 chance of getting the right door and 3/4 chance of getting the wrong door. So if I get a right door, I will go to the next level or next stage, I can say. So we will lose 1 corridor and 1 door and 1 button. So we're gonna be left with 3 different corridors now. So I have to do this in a nested fashion. For example, this is the success part over here, and this is the failure part. I know that there's a 3/4 chance of failure, which will cost me 2 minutes, and I will go back to where I started, EX1. However, there's a 1/4 chance of winning, getting the right door, which will again cost me 2 minutes. There's no change there. But the difference is now I'll be upgrading myself to the second scenario. So instead of the first one, I am going to go to the second scenario. So I have to check the second scenario. In the second scenario, I have 3 paths. One of them is correct. So 1/3, 2 times the third scenario, expected value of the third scenario. And 2/3, the failure rate, 2 times expected value of the second scenario. Now, these expected values are our times that will pass from the start of the scenario to the end of the game, not just for that scenario, for that time. It's till the end. So because it's till the end, these values are here. Now for the third one, there's 2 paths left. 1/2 chance of getting this one, the negative one. The positive one, and 1/2 chance of getting the negative one, not finding. This is the wrong solution, this is the right solution, this is the wrong solution. So this one will update or upgrade you to the last path. This one will just keep looping you back to your starting point in this path. Now, in here, if there's only 1 path left and that's the true one, there's just 2 minutes left. So you have to just go and push it and come back. That's it. In 2 minutes, it's going to be done. However, all I have to do from here on, however, I have 3 more to solve from. All I have to do is just pick this 2 up and put it over here. So I can just solve this one, which is going to give me 6. So I can just take this 6 and put it over here. I'll solve this one, which is going to give me 12. And I'll take this 12 over here and put it in here and here. And I'm going to see that, I'm sorry, to take this 12 over here and put it in here. And I'm going to see that the EX1, the time that I need from the start of the game, let's say, start of the time, till the end of the game will be calculated as 20 minutes. Now, this is a next nested example. You could have solved this one by one as well. It's possible. You will see what I'm talking about in the next exercise if I'm not wrong. But still, you can do this nested or one by one. They are both okay. Now, in this one, Akkuyu nuclear power plant has gone critical and is facing imminent disasters. Okay, we have disasters again. The cooling system consists of 2 independent cooling reactors need to be reactivated to prevent this disaster, and the electrical technician has lost his map of this huge complex. The technician leaves his workstation to face 4 roads, 2 of which lead to the 2 cooling reactors, both of which must be manually reactivated. The other 2 roads do not lead anywhere related to the cooling system, and the technician comes back to his workstation each time he has used one of those roads. All 4 roads take 1 minute to walk to the end and 1 minute to come back to the workstation. The manual reactivation also takes 1 minute to complete. What's the expected time of system reactivation? Now, in this one, we again have 4 different roads, but we have 2 different scenarios. If the roads can be marked. Okay, we can mark the roads so we know which one is correct or which one is wrong. But B, we don't mark the roads. We don't know which one is correct or wrong. We just keep picking one at random. So for the first one, if we can mark the doors or the corridors, we don't, or the roads, whatever, we don't need to, rely on probability. Okay, we can just say, of course we will rely on probability, but we can just say that we have different ways of doing this. For example, if the cooling reactors are, the rooms are decoded as C1 and C2, if I pick C1 first and then C2, then I'm done, C1 and C2. Or if I pick C2 first in the first trial and C1 in the second trial, then I'm done again. But the thing is, these things can be done in many different ways. For example, C1, E1, empty, E, E1, C2, E1, C1, C2, E1, C1, E2, C2, E1, E2, C1, C2, C1, E1, E2, C2. So there are six different ways of doing this, and all of them have different ways in themselves. For example, when I say C1 and C2, it's the same thing as C2 and C1, but still two ways of doing this, going this path. So what I need to do is calculate all of them, all the probabilities and all the number of different ways you can do this. Something like this. C1, C2, there are two ways of doing this. C1, C2 or C2, C1. C1, C2 itself has 1 over 12 probability. Why? Because there's a chance, 1 over 4 chance of picking this one, and there's a 1 over 3 chance of picking this one. Because I already know which one is C1, so there's only 3 paths left I can pick. So 1 over 12. This road takes 5 minutes. Why? C1, going there, 1 minute. Cooling, activating cooling reactor, again 1 minute, which is written in the question somewhere. So as you can see, all flows take 1 minute to walk to the end and 1 minute to come back to the workstation. The manual reactivation also takes 1 minute. So going there, reactivation, coming back, 3 minutes. Going there, reactivation, 2 minutes. You're done. You don't need to come back, okay? The system is online now after the reactivation. So it's 5 minutes. Over here, 3 minutes, go, reactivate, come back. 2 minutes, go, come back. 2 minutes, go, reactivate, come back. 4 different ways, because C's can change places and E's can change places. So 1 over 24 probability, 1 over 4 times 1 over 3 times 1 over 2, 7 minutes, 3, 2, 2. Or E1, C1, C2, again 4 ways, 1 over 24 probability, 7 minutes. And with all 4 of them, E1, C1, E2, C2, 4 ways, 1 over 24 probability, 9 minutes, etc. Now, as you can see, all these values are going to be added up to find the expected passage of time, which is going to give us 7.17 minutes. Now, if the roads cannot be marked or remembered, so I'm choosing them randomly. At the start, we have to find how many times we spend, okay? For example, at the start of the, question, we have 2 correct paths and 2 wrong paths, which means that our chance of picking a correct path is 1 over 2. And our chance of picking a wrong path is 1 over 2 as well. So 1 over 2, 3 minutes, pick the correct path, gone for 1 minute, 1 minute, repaired for 1 minute, and went back for 1 minute, so it's 3 minutes. Or I'm going back. I've chosen the wrong one, spent 2 minutes, and have come back. Now, from here, I can say this 5 minutes for this stage, okay? The first stage where 4 corridors are available will take approximately 5 minutes to complete. On the other hand, when I've completed this one, in the second stage, now, the cooling reactor that I have found in the first one is now a wrong path. The path is not deleted, the path is still there, but it's a wrong path now. So my success rate is now 1 over 4, because there's only 1 cooling reactor left to, repair. So it's 1 over 4. Now I have to take into account the, failure rate, which is 3 over 4 as well. 3 over 4 times 2 plus EX, because I've gone to the wrong place and I've come back. I haven't done any, operations there. And then I have 1 over 4 times 2, because I'm going to the last cooling reactor, and repairing it, and I'm done. I'm not coming back. So 1 over 4 times 2, which is going to give me 8 minutes of time spent. The total will be 5 plus 8, which is 13 minutes for this type of exercise. Now, the last question. It's Batman versus Superman. Batman and Superman are lost in two different mazes. Batman decides to walk through the corridors of the maze using his superior detective skills, because he's the best detective ever, and technological gadgets, whereas Superman decides to pick a side and start bashing through walls to reach that side because he's all bronze. So, but he has brains as well. Still, Batman is facing three corridors, each of which have a 0.4 probability of leading him to the exit in 15 minutes and 0.6 probability of leading him back to his starting point in 20 minutes. Superman, on the other hand, can reach any side of the maze, which has 4 sides in total, and only one of them is the exit, by walking through the walls in 10 minutes. If the side he has reached is not the exit, he flies back through the hole, back to his starting point in 5 minutes. If X and Y are times spent in the maze by Batman and Superman respectively, find which one is expected to leave his maze first. Now, let's start with Batman. We're going to have to find the EX, okay, expectation of X. Now, Batman has 3 corridors. He's going to pick one of them randomly. So, after he has picked that corridor, he has a 0.4 probability of going out to exit, whichever corridor he chooses. So, corridors don't matter. Okay, 3 times 1 over 3. It's just 1. I'm just going to skip picking the corridors then. But when I pick the corridor, I have a 0.4 chance of going out in 15 minutes. Okay, so 0.4 is my success rate. 0.4 times 15 is the expected time of passage there. And 0.6 probability of going around, okay, for 20 minutes and coming back to starting point. So 0.6 times 20 plus EX. Okay, Batman's, passage time of passage. So you can see here, this is for Batman. 0.4 times 15, 0.6 times 20 plus EX. From here, we can say EX is 45 minutes. So Batman spends 45 minutes in there. With Superman, you have 4 different walls, and you're knocking them down. So when you return, you will notice that that wall is broken. I'm not going in there. I have to pick another one. Simple. So this is the nested version. This is the open version. They are actually the same things, but still, in the nested version, you have in the start, you have 1 over 4 probability of getting out in 10 minutes, but you have 3 over 4 probability of not getting out in 15 minutes and picking another another corridor, which is 1 over 3, and getting out in 10 minutes and not getting out in 2 over 3 probability with 15 minutes. And then you're picking another door, 1 over 2, and going out in 10 minutes, or you're picking another door and not going out in 15 minutes, and then you're picking the last door and going out in 10 minutes. This is the nested version, which is going to give us 32.5 minutes. Or I can just calculate the value of each floor with respect to each other. This is nested as well, but not as chaotic as this one. For example, for EY1, I know that from the first time Superman starts till the end, we have 1 over 4 probability of picking the right door and going out, times 10. Or we have 3 over 4 probability of picking the wrong door, spending 15 minutes, and going to the next stage of the question where 3 doors are left, 3 corridors are left, 3 walls are left. Right? Doesn't really matter. So with EY2, we have 3 doors left, or 3 corridors, which is picking the right door gives us the probability of picking the right door as 1 over 3 times 10, or picking the wrong door or corridor 2 over 3 times 15 plus EY3, where EY3 is the third stage where I have destroyed 2 doors and 2 doors are left, which is going to give me the success probability of 1 over 2 times 10, or failure probability of 1 over 2 times 15 plus the expected value of the fourth stage. So which is the last stage, and there's only 1 door, which is 10 minutes. So put 10 over here, you will get a number. Put it over here, you will get a number, and put it over here, and you will get the 32.5 minutes of time spent by Superman. So basically, Superman is faster than Batman in this question.